Welcome everyone in Cardano room. We have a great lineup of speakers this morning. And it is my pleasure and honor to introduce the first speaker today, which is Andrea Palladino, Senior Data Scientist in GSK. He also is, I would say, an influencer on LinkedIn. Is it correct to say? You should follow him. He talks about a lot of interesting stuff, not only AI. And he will talk to us about, from physics to human sciences, the universality of machine learning. Thank you, Andrea.
Thank you for the introduction. So yes, today I will talk about various topics to show how the machine learning can be used in different aspects. I will start. So I'm currently working as senior data scientist in GSK in Siena. I'm not here today to talk about my work in GSK. I will touch some point, but I'm here more in my name, I would say. My background is in physics, so I did a journey from physics to artificial intelligence. In this talk, I will present a brief history of AI/ML, since I'm the first one to speak in this room. Then neural network applied to physics. That was my first touch point with machine learning. CNN applied to astrophysics, and then other aspects like federated learning and natural language processing that I'm using today in my daily job. This is an image from my bachelor thesis in physics 14 years ago, in which for the first time I used in my life a deep learning algorithm. I will tell the story later. And this is what I'm doing today. Today I'm mostly working on natural language processing and deep learning applied to DNA sequences. So it looks very different to what I studied, but I will show that there are lots of many common aspects between these different things. I like this slide because today I think, especially in the last year after ChatGPT was released, I would say many people changed their job and became AI expert. So I think there is still a bit of confusion between what is AI, ML, deep learning. I like this slide from Coursera, this image, because AI is very general. It's everything that we can run on a computer to solve whatever problem, while machine learning is more refers to something that learns from experience, so from training, test, and improving. And deep learning is basically neural network. It's the new name of neural network. We can also find this definition on the MIT blog. And it's interesting to notice that the theory of neural network was there 70 years ago. So it's not maybe even more, 80 years ago. It's not something new. The theory was really there, but you see in this figure that there was some progress of AI. Then there was there was the first AI winter, then some progress again, then AI winter, and the major problem was not the theory. This is also a book that I used in my bachelor thesis in 2010. And all the theory of neural network, except for more specific thing like, I don't know, the dropout, some regularization function, everything was there in this old book that it's called Introduction to Artificial Intelligence. The main difference, I think, the first game changer was the introduction of GPUs. So it was a more technological problem. In 2012, there was the introduction of this neural network, AlexNet, for image classification. This was the first neural network that was using GPU. And I think this was really the first game changer in the field. Because you see that now, of course, we have much very high performance NVIDIA cards. You see on the right one of the video cards that you can buy for something like $1,000, and the performance is already a factor 10 higher than the old video card. And you can notice, since I also like bit finance, you can see in this plot what I'm trying to explain if you are not convinced by the previous slide. You see that NVIDIA stocks, the price was around 30 in 2016. Then there was the Bitcoin that arrived into the game, and you see that there was the first increasing of NVIDIA, because Bitcoin mining requires a lot of computational power. And then there was the COVID, and NVIDIA increases again, because with COVID, the remote working was used by many people in the world. There was a crash in 2022 due to the war, but then there was ChatGPT. And you see here that NVIDIA basically started, there was factor 10 less than Intel, and now it's a factor 20 more. So it's times 200 compared to 8 years ago. So that's why I think that really NVIDIA changed the game in the AI field. And the second game changer, I think it was reinforcement learning. I like a lot reinforcement learning. We are also using it to try to solve some biological problems. Reinforcement learning was introduced in 2017 by Google DeepMind. And you see here that it was applied first to theory, to games, because reinforcement learning usually is done in a way that you have some action, then you have a state, and you have a reward. So if the action is followed by a reward, the algorithm learns that this is the right action to do. And that's why this is the way in which the algorithm learns. And this was applied with a great success to chess. This is the image from a DeepMind paper. We have the World Championship on top left. I also play chess, but I'm much lower level compared to the world champions. And you see that AlphaZero, that was the reinforcement learning algorithm that was trained to play chess, after a few minutes was stronger than me, after a few hours was stronger than the world champions, and after a couple of hours it was stronger than any other chess engine in the world. That was Stockfish at that time. So reinforcement learning is really something really, really powerful that can be applied to various fields, not only to the game theory. And of course, the third game changer is generative AI. I will not spend so much on this part because I'm not an expert on it. I only want to highlight the fact that I read more or less every day. We are producing our generative AI from scratch, but if you try to compute the cost to produce a generative AI at home, it's it's extremely high. You see that ChatGPT was trained on the 25,000 GPUs, really powerful NVIDIA video card, $10,000 per video card. You need really a terabyte training set and really a huge number of parameters. So you can really, it's more or less impossible to do that from scratch, but you can for sure adapt the already existing model. So the fine-tuning has shown to have great success. You can see here that there are some fine-tuned. Yeah, for example, here you see that there are some, it works okay, some fine-tuned on some topics, and they work really, really well, much better than the original ChatGPT. Okay, let's come to machine learning. This was my first experience with neural network, as I said. I applied it for my bachelor thesis. It was an argument of physics to model an ion implantation machine. We are in the field of semiconductor. This was to model a machine in which you want to increase the performance. At that time, it was 2010. I tried to write the algorithm in Fortran. I think this is a language that only physicists use. I don't think there are other people in the world that still use Fortran 90. TensorFlow was not there. TensorFlow was launched in 2015, also PyTorch in the same year. So it was really hard. If you try to implement from scratch a neural network in Fortran, you will realize that it's not so easy to do. So after 1 month, I understood and was going on the wrong direction. That's why I used, it was a proprietary software at that time. The name, I think it was Synapse. You see that was quite a simple neural network, 27 input parameters with one hidden layer with 4 nodes, another hidden layer with 6 nodes, so nothing really complex, but I remember the computational time was quite a lot, even with this small neural network. But the result was quite good. We got 95% R-square in tests, so the result was satisfying at the end. The problem is that we also had the possibility to reach our goal, so to increase the performance of the machine. We understood how to vary the parameters, and we also checked experimentally that this was working. So I think it was a nice application. Unfortunately, when I presented the thesis, the commission, there were some people that told me, okay, this thesis is too exotic for a bachelor thesis in physics. We don't like it. Well, I remember one professor of theoretical quantum field theory told me, okay, this is really rubbish. And another one told me, okay, this is the future. So now we know which one was right. But I understood from this, my bachelor thesis that, in university, in academia, usually you cannot be too in the future. I mean, you need to stay a bit with more standard things. But then I continued to be interested in these topics. Here we see an example of the first convolutional neural network around 1996, 1998. This was it's called the LeNet-5. It's a convolutional neural network with 5 layers, 2 convolutional, 2 fully connected, 1 output layer. And I proposed at some point to use it when I was in my postdoc in physics to analyze these strange objects that are in the universe that are called blazars, active galactic nuclei. So you know probably about black hole. Black hole are objects in which nothing can escape, even light. Those objects are really interesting from the point of view of the astroparticle physics. I proposed to use convolutional neural network to study these objects, particularly this image that you see here, bottom left, that it's called the spectrum. Also in this case, it didn't work. So they told me, no, this is impossible. A few days ago, I've seen this paper. So they applied now today convolutional neural network to study spectral blazars. So it worked, but when I proposed it, it was too early, probably. So I understand that academia is probably too slow to react to the external world. It was not really my world. That's why I decided to move into startup industry. And I joined a startup in 2020 in Berlin, in which I was doing federated learning. This is a very interesting topic because we are all using federated learning basically every day, even if we don't know that. Federated learning is a collaborative learning, is distributed learning with multiple clients that are collaborating on training the models. A bit of water? No. Different clients agree on a certain architecture, neural network architecture. Then each client trains the model using its own data. Then the weights of the neural network are sent to some central server aggregator. The weights are aggregated, and then the clients do different epoch of training, starting with the aggregated weights. It's interesting to notice that with federated learning, you can reach very high performance, more or less the same level of performance that you would reach with all the data in one place, by not compromising the privacy of the data. So this is the power of federated learning, that you reach very high performance, but you don't need to send the raw data. So when there are multiple companies, industries that want to collaborate, federated learning is a great choice, and it works very well. Of course, there can be problem also in this case, problem like the inference attack, for example. You can try to guess the data from the weights of the neural network, or you can have data that are non-identically distributed. This is more a statistical problem, but in this case, federated learning would not work so well. But generally, federated learning works well, and it is used even by Google, for example, in the Google board. So when you write a text and you see the prediction of the next word on your smartphone, this works because the algorithm was trained using federated learning. So it was trained using the information on all the smartphone from different users. And the process is basically this, that you send your data, even if you don't know you are sending always the data, and then you contribute to this huge algorithm of distributed machine learning. The server takes the average of these new models, and the weights are distributed to other clients. Let's come to more to things that I'm doing today. Today I'm working mostly on natural language processing and deep learning. Natural language processing, I'm applying, as I said in introduction, to DNA sequences. I don't know anything about biology, but it's not necessary to know something about biology, because the point is that a DNA sequence is basically a text composed by these 4 words, A, C, G, T. And once you have a text, you can apply the same method that you have for a human text, for text that you can read and understand. We see here different text. For example, this is good, this is bad, this is awesome. How do we convert this text into numbers? So we build a matrix in which in the columns we put all the possible words that we have. So in this case, we have 5 words. This is good, bad, and awesome. And then we count how many times the word appear into the text. So for example, the first sentence, this is good, is transformed into 11100. This is a very basic example. You can, of course, combine different words. It's not only a single word, you can combine 2, 3 words, so you are not limited to one, of course. And to have a good algorithm, you need usually more than 1 word. You see on the right a possible graphical representation of the matrix that I previously explained. The higher is the dimension, more important is the word. Usually we are not interested only in the frequency, but more in the importance. And the importance is obtained with this equation. So yeah, don't worry too much about that. But basically here we divide by how many times a certain word appear in the entire document. And this is because there are some words, like, for example, I don't know, and, or, then, words that appear a lot in the document that are not so important. So you are more interested to unique words or to words that are present in few documents. This is an example of sequences. Those are just fake sequences, not real sequences. You see that we have these 4 characters, and with the technique that I explained before, we can build a dictionary in which in the columns we put different words. In this case, I'm only taking as an example all the combination of words between 3 and 4 characters. You see that we have 320 in total. Then we compute the frequencies. And then you have this matrix. So we have converted, in this example, 750 sequences into a matrix that has 750 rows and 320 columns. And now you can just use the usual machine learning algorithm. For example, this is just a toy example in which I built a data set in which I say if there is this TA subsequence, then assign label 1. If there is not, assign label 0. And you see that if you run a random forest classifier, you get 100% accuracy because it's really a trivial rule. So the algorithm can immediately recognize what the rule is. But this works also with real world problems. So this is okay, there is one plot missing, no problem. But it works also with real problems. So we applied it to to real sequences, to bacterial sequences, and we got very high accuracy. We got a paper accepted a few weeks ago. Another alternative approach is to divide the entire sequence into fragments that are called k-merts. So you see here, for example, k-merts of length 6, and then you can pass these fragments to the algorithm as individual words or combination of words. This is an example that you can find on Kaggle. Kaggle is a nice website that I suggest quite often to data scientists because you can find a lot of data sets, a lot of competitions. And if you are interested in applying machine learning to this field, you can try this competition here in which there are 7 classes with different DNA sequences. You can apply the technique that I described. So divide the text into subsequences, apply a dictionary, and then apply a classifier that can be a random forest, or we used XGBoost. XGBoost work very well. Also, the CutBoost classifier is very strong in this kind of things. And then there is the deep learning that is also largely used in this field for analyzing sequences. Particularly, NLP does not work so well for DNA sequences when you need to preserve the order. Because if we go back to this matrix here, you see that we count the frequencies. And we see, for example, that the word in the first row, TTG, appears 5 times. But we have no idea where TTG is located. So we lost completely the information on the order. If TTG was at the beginning of the sequence, in the middle, at the end, we don't know. There are some cases in which you need to preserve the information on the order. And this is the case in which a neural network can be the right algorithm to use. And to use a neural network, there are various techniques that you can use for converting the sequence to numbers. One is the label encoding. Another possibility is the one-hot encoding. And then you can pass the matrix to the bidirectional neural network, for example. If we want to apply the one-hot encoding, the way is the one that you see in this figure. So we have the usual 4 characters, A, C, G, T. We build our matrix. And we put 1 when this nucleotide is present. Those are called nucleotides, ACGT, and 0 when it's not present. So the first sequence, for example, it has A in the first position, then C, then it has A, and so on. So we have 1 matrix for each sequence. But a matrix, if someone is doing computer vision, knows that a matrix is an image. So you can convert the matrices into images. You can even reshape them because usually they are rectangular matrices. So you have 4 rows and many columns. You can reshape in a square matrix. You can convert into images. They will look like these QR codes that you see here. And then you can use the usual machine learning algorithms that you use for image recognition, for example, convolutional neural network. This is an architecture taken from a paper in which they apply convolutional neural network. So you see here that we have 2 sequences that interact each other. It's microRNA on the left, genes on the right. Both are converted into images. Then there is a convolutional neural network, a max pool, and then the usual things, bidirectional neural network, dense layer, and logistic regression classifier. And this is a way to use deep learning in this field. An alternative is also to use the pre-trained language models. Probably you know BERT. BERT is quite common in language models now. In biology, there is the version of BERT called DNA BERT. So DNA BERT is a pre-trained bidirectional encoder. So this is an algorithm that you can use to convert the sequences into some numeric metrics to do the operation that is called embedding. And once you have done it, you can then use other algorithms for the classification. DNA-BERT has also its internal pipeline that allows to do everything from the embeddings to the training, classification, and so on. But you see that deep learning can be used with success also in this field. I want to close my talk with a few words on Formula One. That is one of my passions. I tried many times to enter in this world. I always failed, but one time I arrived at the last interview with Red Bull, so sorry that I failed. I could have been world champions now. And this is a nice post that I found on LinkedIn, in which there is one person that worked on in Formula One, in which he shows various aspects on AI/ML applied to Formula One. And it's usually, especially today, AI/ML is used a lot in Formula One for example, fluidodynamics simulations, but even for things like the race strategy. And yeah, for fluidodynamics simulation, you see here the Navier-Stokes equation. So those are the equations that all the people that have done physics or engineering, they studied somewhere during the university. And these equations are used for simulate the behavioral fluid, or usually they are used for aerodynamics simulation. They are usually called CFD, this kind of simulation, to simulate their flow around the car. And the problem of this equation is that, so those are partially different equations. They are quite hard to solve. You can do numerical simulation, but they are hard and heavy. But today, machine learning is applied also in this field. We have here a paper that is of 2021, in which they show that they can use with success a convolutional neural network, even in this field that looks very far away from what I've described before. But the application that I liked more is this one. You know OpenAI for ChatGPT, but OpenAI is producing very interesting libraries since several years. There is this library, it's called GYM, to apply reinforcement learning. It's also quite easy to use if you want to build some reinforcement learning on games. There are also pre-trained games that you can try and you can fine-tune, like the old games of 18, I don't know, the space shuttle, things like that. And there is a paper in which they used OpenAI GYM library to simulate various conditions in the race using the reinforcement learning approach. And you see that, if you remember one of my first slides, they are really using the reinforcement learning setup. So they have some inputs, they have some actions, and then they have the reward. The reward in this case is just the final position in the race that will give a certain amount of points. And the action can be, for example, the pit stop at a certain lap. So you see that it's not limited reinforcement learning to games, but it can be applied also to real situation with success. I think I'm on time for the conclusion. So in this talk, I tried to cover different aspects of machine learning that can be used in several fields. I started from physics, where I did my bachelor thesis using the neural network. And then I show how we can apply also convolutional neural network to astrophysics. Some words about federated learning and more recent things like natural language processing and deep learning applied to DNA sequences. And thank you for the attention.
Thank you very much for Andrea for the talk and for the excellent time management. You finished 30 seconds before the exact 30 minutes. So we have some time for questions from the audience. Who wants to go first? Stefano, go ahead. Yes, I'll come to pick to give you the mic so that also for the streaming it works.
Andrea, thanks very much for this interesting talk. That was great. My question is mainly from your musical education. So, curiosity: have you ever tried to apply AI or ML to any music, either generating music or finding patterns in music, something like that? Or do you know anything that it could be interesting to read?
Not personally, but I have a friend of mine that has a startup in which he does exactly that. He produces music for video game using AI ML. So I can give you the contact if you're interested in that.
Okay, who's next? Who wants to go next? Yes.
Hi, Andrea. Thanks. I want to ask you, what are the use case of these application of NLP on genomics? I mean, you show how to do it, but what's the purpose of doing it?
I don't know if I can answer today, but maybe.
Yeah.
Maybe. When you do things like that, applied for, I don't know, some bacterial species, for example, you know that you have a vaccine with a certain efficacy on the bacterial species that you have detected.
Okay.
But you don't know anything on the new strains that will come in 1-2 years. You can think to COVID, for example. COVID is a virus, it's not a bacteria, but it's the same thing. Yeah. We had a lot of variants, and after you have built a vaccine, you don't know if this vaccine will be efficient on the new variants. Once you have trained an algorithm like that, you can simulate what will be the efficacy on the new variants. So you can you can know in advance, for example, if this vaccine will work or not. But you can even modify the vaccine to be more efficient with the new variants. So both sides, it's both on the prevention side to understand if it will work or not before the new pandemic or new spread of the new strain, and also trying to modify and adapt the vaccine for the new strain.
Okay, and how you precisely do it, just for the sake of the...
Coffee break.
Yeah, your coffee break, okay. Okay. Thank you.
Okay, keep them coming. Who's next? We had a lot of topics touched by Andrea. I'm sure you're curious about something.
Hi, I was impressed by what your professor told you about your thesis. The one that said this is rubbish, and the other one that said this is the future. I've seen sometime discourse about the application, the modern application of machine learning to scientific research as being something like a movement toward more engineering than science. So what do you think about this kind of approach from, philosophy of science point of view? I mean, we can find great solutions using machine learning, but isn't the science part of things a bit different from just finding solution without a specific law that gives us a clear explanation of why things work the way they work? Yeah.
Clearly understand your point. I think we have to distinguish two things. It was 2010, so it was not, let's say, the hype to use the neural network on machine learning. So it's reasonable that a purely theoretical physicist that uses only equations, not to make theories and solutions, do not like this approach. Today, probably there is the opposite problem. We rely too much on that, and we are not advancing in the pure theory. So we are trying to find the approximate solution to everything. Yeah, I perfectly know what you mean. I don't know if there is a way to solve it now. I think we are getting worse because even now we are using ChatGPT for trivial things like, I don't know, write an abstract. There was a paper a few days ago with an abstract written by ChatGPT, and both the authors and the reviewers did not notice that. the paper starts with, certainly, I can write an abstract for you, and then there is the abstract. And this was accepted and published, you see what I'm saying? So, I understand your point, I don't know how to... Yeah.
Okay.
I agree with you.
Other questions from the audience? Who wants to go? We are great on time, so we can take a few moments. If no one else has a question, I'll ask a question. So, in one of the first slides, you showed the AI, in the AI winter slides, in which you showed the progress, the initial progress in AI. Where are we? Okay. Yeah. Which, if I'm not wrong, one of those peaks was a different technology of AI, symbolic AI, and then at some point, since the last winter, let's say the technology was based on neural nets. So, in your opinion, and we know, I mean, that everybody can make mistakes and predict rubbish or anything, do you have an opinion on whether or not there will be an AI winter, where there'll be a resurgence on other methods, or a combination between connectionist and symbolic approaches?
I think in the next 1-2 years, we will talk, I mean, generative AI is now the hype, but I'm not sure that this will be forever. I mean, probably there will be some, at least from my point of view, I expect a generative AI winter somewhere, and something different that we don't know today will jump on the field. This is my impression. There is too much focus on that, even for topics that cannot be really solved with generative AI. They want to use that for everything, so I think, I don't know, I would not be surprised by a generative AI winter of some years and something else that jump into the field.
So we should not be too worried that robots are coming for us, because winter is
maybe
coming.
I'm completely wrong, and next year we will have a conference of robots, I don't know.
Okay, thank you, Andrea. Let's thank Andrea once again.